Hello my test tubes and welcome to Cambridge Chemistry Challenge preparation video. In this video I'm going to be going over the 2019 Cambridge Chemistry Challenge. I think the mark schemes available online are actually fairly self-explanatory. I think what I have to offer with this video is more how I would go about thinking about a particular question rather than the solutions themselves. So starting with one, what is the oxidation state of indium in In2O3? I usually do this with 2In, where In indicates the oxidation state of indium, plus 3O is equal to 0, and O indicates the oxidation state of oxygen. This gives me 2In minus 2 times 3 is equal to 0, so 2In equals 6, and In equals 3. For part 2, I'm having pure indium react with nitric acid and it produces a flammable gas. Without thinking about the flammable gas, I'm just going to go and write what I think it would be and then figure out if there's a flammable gas in there, and if that's it, then I'm all set. So this gives me indium plus some number of HNO3 gives me indium, and then the indium salt. I have no information of the oxidation state of the indium salt apart from the fact that here it was a +3 oxidation state, so I'm going to assume it's the same because that's all the information I'm given. So that's NO3, 3, giving me 3 of those, plus H2 times 3 over 2. And oh wow, hydrogen is a flammable gas. Yay, I don't need to go any further into that. For part 3, I believe I have to say which species is oxidized. Well, indium goes from 0 to +3, so that's oxidized, and hydrogen goes from a +1 to 0, so that's reduced. Then for part 4, I'm not going to write that down because it would take ages. For part 4, with hot nitric acid or with more concentrated nitric acid, the only gases formed are oxides of nitrogen. It's important to note that it's the only gases formed. I'm going to use that later in the argument and give the equation of the reaction of indium metal with nitric acid forming only nitric oxide, NO. Well, indium metal plus some number of nitric acid, HNO3, gives me the same salt, so InNO3 by 3 plus NO, and no other gases, so I don't know what to do with my H's apart from convert them to H2O. And here, I think that's pretty much it. So all I have to do is balance the equation. This gives me 2 and 4, and I think that's it. For part 5, formation of indium hydroxide from indium nitrate is In just a simple salt substitution. I don't know, just the thing where they change the ions and the salts. InNO3, 3 plus some number of NaOH gives me the same oxidation of indium, InOH, 3 plus NaNO3, so that's going to be 3 of each. 4, 5, 6 Vi, wow. Give the equation of the formation of indium oxide from the hydroxide. So just looking at the hydroxide, InOH, 3. I don't know whether there's going to be an extra oxygen added, so I'm just going to put a no 2 and I'll delete it later if I need to. Then In2O3, so I'm just going to add another indium here, plus H2O, and if I add the correct number of hydrogens, so that gives me 3H2O. I actually find that the equation is balanced without the extra oxygen. I'm going to get rid of that one. For part 7, the mass, I need to calculate the number of the mass of indium oxide produced from 1 gram of indium metal. I know that the standard mass of indium is 114.82. That's from the table above, and from here I get that the number of moles of indium is going to be 1 over 114.82, which is about 8.7093 times 10 to the minus 3. I keep lots of extra significant figures because I think that makes my end calculation more accurate, and then I reduce them when I need to give the answer. And because each of the indium oxides has 2 indiums, there's going to be 8.7093 times 10 to the minus 3 over 2 moles of indium oxide, and the mass of indium oxide is going to be 114.82 times 2 because there's 2 indium, plus 16 times 3 because there's 3 oxygens and the mass of oxygen is 16, which is equal to 1.21. For part B, a certain mass of indium is converted to a certain mass of indium oxide, and assuming different formulae for indium oxide, I'm supposed to try and find the mass of indium. So what I'm going to start with for part I from B is the number of moles of indium, so the mass, 0.5135 over the molar mass of indium, is equal to the number of moles of indium oxide, so that's the mass of indium oxide, 0.6243, divided by the mass plus 16, which is the molar mass of oxygen. That's going to give me 0.5135 m plus 8.216 is equal to 0.623. And then subtracting the m's, I have 8.216 is equal to 0.1108 m. Dividing by 0.1108, I get 74.2 equals m. Assuming the second one, I still have the same equation, well, nearly the same equation. 0.5135 over m is equal to 0.6243 over m plus 32 instead this time. So, solving again, I have 0.5135 m plus 16.432 is equal to 0.623, and subtracting, I get 16.432 is equal to 0.1108. The quick maths people among you might have spotted that it's twice the mass already, but then dividing by 1108 and dividing by 0.1108, I get 148.3 equals m. For part 2, section 2, part C, we have that iodine has atomic number 53 and atomic mass, as we have read, 127. You get the atomic number from the periodic table. So it has 53 protons, 53 neutrons, and 127 minus 53, giving 74 neutrons. Then for part D, I'm going to let x be my percentage, and so that's not a fraction of the total number where the total number is 1. That's actually going to be like x equals 37%. So that means that x times the the percentage of Thallium-130 times the mass of Thallium-130, 129 times 0.90623 plus 100 minus x times the mass without the Thallium-130, so 126 for 12449. all divided by 100. 100 gives an average of 127.6. So, multiplying everything by 100, we get, and cancelling the x's out, we get 100 times 126 point something, so 12641.2449 plus 3.11 93774x equal to 12760, and so 3.119377 is equal to 118.7551, and dividing by 3.11 something, we get x is equal to 33.99, so that's basically 34. Then moving on to section 3, giving the equation of the reaction of thallium 3 nitrate with potassium iodide. So thallium 3 nitrate would be TlNO3 3 plus Ki, some number of Ki, gives TLi plus KNO3 of some form. If we balance the NO3s, we have 3, and then the Ks, we have 3K, and because we don't want to multiply the TLs, we have 2 extra I's, and that forms I2. I don't respect this question because I feel like the reasoning behind adding the extra I2 at the end doesn't really make sense. It's like, if you're lucky, you'll think of that. If you're not lucky, then you won't. So it's not like a brain question, it's more like a chemistry question. I'm not a huge fan of. But continuing on. F part I, the oxidation state of cesium in cesium I3. This makes me think that it's a 3 plus, because I'm thinking that the iodine each have -1 oxidation state, but then if you look at the next part, it's what the average oxidation state of the iodine is in these compounds, and I'm fairly sure they wouldn't ask me that if all the iodines were 1 minus, so I'm going to instead assume that CS is in its normal oxidation state, so +1, and iodine is, the average state of iodine is going to therefore be -1/3, so that 1 minus 1/3 times 3 equals 0. After that, draw a dot and cross diagram showing the structure of the anion present in CSI3 and TLI3. This suggests that the anion is the same in each one, which means that it's either I2, I, or I3. The thing is, CS is probably going to stay in its own because it's a really good cation by itself, so it's probably going to be I3. Also, the ion drawing actually comes up every year, and it's usually quite a big ion, as in not quite a big ion in terms of size. It's usually an ion that you might expect would show up. So it's relatively obscure, but it's not obscure enough to not find on the internet. So just the night before, Google all the ions you can imagine and try to memorize them, but not too much because it's probably not going to show up. One of them will, but not all of them. So don't spend ages memorizing them. Just have a look at them and be like, yes, I remember this trick and this ion. It's really useful. Looking at the iodine, if you hadn't come across the iodine anion before, it's going to have 1 minus, and when wondering which one has the extra electron, it's probably going to be the one in the middle just from symmetry. So, and also each of the iodines will probably not sustain more than a double bond. Just looking at experience about iodine. So if you fill these in normally with no extra electrons, because this is going to be the one carrying the extra electron, you get this, and then you fill the with the correct number of electrons on this iodine as well. as in of its own electrons. It's supposed to have 7 of its own electrons. This gives 1 lone electron, so that's why we'll put the extra electron at the end. The average oxides and the bond angle in the anion present in the compounds. Well, my first idea was actually to put because there's 5 electron pairs surrounding it, it's going to be triple planar. And my first idea was to put the 2 iodines, the iodine in the middle and the 2 iodines separated by 120-degree angle, because the lone pairs are the ones that repel most. However, and this would give me 2 lone pairs that are repelled by a 180-degree angle. However, I then realized that the angle between these 2 lone pairs is going to be 90, which is less than what it would have been if the 3 lone pairs were around here. So it's actually going to be linear, and the lone pairs are going to be here. Section 4 really pleased me because it had the illustration of the original, I mean not the original, but the periodic table that actually Russian students use. I mean, they don't use exactly that one because everything's been changed a little, but that's pretty much the form that the Russian periodic table takes. It didn't actually give me any extra advantage, as you can see by the questions. They don't really look at the periodic table that much. But it was still cool to see. For G, part I, that's just averaging out nitrogen oxide and iridium oxide. If you want them to have a +5 state, then there's a 5 state, then there's going to be an N2O5 that gives a +5 average state, and then NB2O5 does the same thing. For part 2, when they suggest a structure, it's usually going to be either around 1 atom, in which case you just look at electrons and how they behave, and if it's around 2, then there's lots of different shapes it can take. But because there's exactly 2 nitrogens, I'm willing to bet that it's going to be symmetric about the 2 nitrogens. So it would make sense to think double bond, double bond, double bond, double bond, and then O, but also any other symmetric molecules forming nitrogen. Just look for symmetry. There would also be O, 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 and then double bond, or just 5 O's like in between the 2 nitrogens. However, if you try to visualize this in space and then try to visualize this in space, this guy seems much more likely. So just draw this guy. But then you might realize that the nitrogens that are here nitrogens don't usually form 5 bonds. So how about looking at a dot and cross diagram? This is going to cost you quite a bit of time, but if you don't know what to do here, then I think it might be worth it, unless you're really good at organics. But anyways, so single bond with the oxygen, single bond with the oxygen. Oxygen does its own stuff with its living pairs here, and then double bond with another oxygen, because that does give the nitrogen its normal triple bond. So no, sorry, double bond is safe. Oxygen, double bond. Sorry. Then here, nitrogen needs to still add 2 of its extra crosses because it has 5 electrons. However, if you add any more dots, then there'll be more than 8. Right now there are exactly 8. So O can just chill here with its own electrons, and O is actually pretty happy with that. So nothing bad here, and it turns out the formula is actually O double bond, arrow, O, so dative bond. Right. Solid nitrogen has a different structure from the gaseous form and consists of linear cations and trigonal planar anions. Suggest the formula of the cation and the anion in the solid nitrogen B oxide. So we're going to have something like this, and looking here, you could have something with a bunch of oxygens and you could have something with 2 hydrogens. However, it's more likely that there's going to be a nitrogen, sorry, not hydrogens, a nitrogen in there. And because nitrogens are special, they're going to be in the middle, and then oxygen is going to surround them. So the structure for the anion is going to be NO3 minus, because that's the trigonal planar one, and for the cation it's going to be NO2 plus. Don't usually see NO2 there, trying to be like sneaky and stuff. I don't know. Anyways, for part 4, this is just a diagram, so let's have a look. The special energy diagram thing. What's its name? He had a law even for NO2. It doesn't matter really, because you still get, don't know the name, but I still know what to do. Anyways, so there's definitely some energy of formation. So I'm going to decompose that into its normal elements. So that's 2N2 plus 5O2. However, there's also an NO if you look at over here, and an NO2. So I'm going to form an NO with this. So that's going to be 4NO plus 3O2, and then from here form the 4NO2. And this one is simply the negative of the delta formation, so that's minus 2 times 11.3. Here we break 2 nitrogen bonds, so that's 2 times 945. We break 2 oxygen bonds, and that gives me plus 2 times 498, and we form 4 NO bonds, so that gives minus 4 times 631. And then in the final part, you form from the NO and the O2. Basically there's force reactions of the form that you see in this line, and so it's going to be minus 58.1 times 4. And if you sum that, so minus 2 times 11.3 plus 2 times 945 plus 2 times 498 minus 4 times 631 minus 58.1 times 4, I think you get 700 and no, you get 100. I'm just looking at the paper that's next to me, which has like answers that I don't know. For part 4, I know straight away the salts formed when a lithium hydroxide neutralizes 1 mole of nitric acid is going to be lithium NO3, and then the other is analogous to the lithium salt formed when 3 moles of lithium hydroxide neutralize 1 mole of phosphoric acid. I'm not entirely sure about that, so I'm just going to do that in case. So 3 lithium OH plus H3PO4 gives, I think, lithium 3PO4 plus 3H2O. And so the first type is going to be instead lithium, and instead of nitrogen, going to have niobidium O3, and for the second one, it's going to be lithium 3 instead of the phosphorus, niobidium, and then O4. For section 4, I remember Peter Wuthers coming over to give a talk at my school, and being like really obsessing over this sculpture they have at St. Cat's. Thought it was quite sweet. For H, give the full electron configuration of calcium and zinc. Just going to scroll up to the periodic table. This gives me, for calcium, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 4s2 all the way up to here. Then for zinc, it's going to be the same, except it's also going to add a 3d10 up to there. So 3s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Returning, given the maximum oxidation states of elements in group 2 and 12 are +2, what are the valence electrons of barium and mercury? And then the same question for given the maximum oxidation state of the elements of group 7 and 17, except fluorine, are +7, what are the valence electrons of manganese and bromine? So, for part 2 first, barium and mercury here both have maximum oxidation states of +2, so I'm willing to bet that the mercury, instead of randomly losing one of its complete shell electrons in the d orbital, will lose one of its s orbital shells, because that would explain why it only loses 2 of them. So that's going to be 6s for each, because that's the 6th s orbital, and then that's for I. And for part 3, that's manganese and bromine. Well, bromine isn't going to randomly lose any of its d electrons, so I think for bromine it's going to be the 7 electrons that it loses are going to be the 4s electrons, and then the 4p electrons, so 4s2, so sorry, 6s2, 4s2, 4p5, 5, yes. And then for the manganese, it can't lose any of its p electrons, so it's just going to end up losing its d electrons, so it's going to be 4s2, 4, 3, d5 instead. d5, yeah. Going back, use the periodic table to write down the full electronic configuration of organoson, the last element of the periodic table. Well, this is going to be fun. So up to S6, I'm fine without the F orbitals, so just going to part 4 gives me 1s2, 2s2, 2p6, 3s2, 3p6. I wish I could sing, then it would actually be nice. 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and now we get the F, so that's going to be 4 F14, 5d10, 6p6, 4 7s2, damn it, 5f14, 6d10, 7p6. Yay! Going back, it is predicted that in order to complete the next row of the periodic table, starting with electrons in the 8s shell, it will be necessary to fill the elements in the first row of the D block. Now, the S block has 1 times 2 orbitals. 1 times 2 orbitals. The P block is 3 times 2. The D block is 5 times 2. The F block is 7 times 2. So it's just going to be 9 times 2 equal to 18. Assuming no orbitals from manganese shells in the 9th period are occupied, to predict the atomic number of the element beneath organoson. That's just going to be the organoson's proton number, which is 118, plus 2 for the S, plus 6 for the P, plus 10 for the D, plus 14 for the D, plus 18 for the G, and that gives 168. So for question 2, part A, I'm going to do the same thing as I did at the very beginning. So 5H, where H is the oxidation state of hydrogen, plus I, plus 6O, is equal to 0, so that means 5 plus I minus 12 is equal to 0, and so I is equal to 12 minus 5, which is 7. Part 2, balanced chemical equation for the formation of metaperiodic acid from orthoperiodic acid. So I have H5IO6 plus maybe something forms HiO4 plus. Now here I see that there's 4 H's, 2 O's, so that just gives me 2H2O, and I don't need to add anything else. For part 3, I have one more oxygen than hydrogens, so what I'm thinking is that I have a whole bunch of OHs, 5 OHs in fact, OH, OH, and OH, and then an oxygen, and this gives me indeed 1, 2, 3, 4, 5, 6, 7, an oxidation state of 7, yay. For part 4, I have only one hydrogen, so I'm thinking an OH, and then a whole bunch of double bond O. And as you can see, this is neither an oxidation nor a reaction, so it makes sense that the iodine is going to be in the same oxidation state. For question B, circle, looking at the reaction here, circle the term that best describes the role of periodic acid in the reaction. So this is basically asking whether this is a reaction as a reduction or oxidation, and well, looking at the functional group level of these two carbons, that they go from each having a functional group level of 1 to having a functional group level of 2. So I'm going to say that that's an oxidation ox. And then C, suggesting structures for these following a sort of, this is basically asking how this algorithm presented to you in this line here applies to the molecules in the example. So here, for this example, we just have the bond for OH. The bond in between the OH is breaking and thus forming a double bond between the O's. So that's just going to be a blue and then double bond O. And for the part 2, I'm going to redraw the structure. OH, OH, thingamajiggy, OH, and OH, and here we're going to have 2 parts that break off, and this gives me this first section is going to give O, this second section is going to give thingamajiggy, and then another O. There's obviously going to be H's here to just complete the thing. I don't draw H's on the circle thing, and then this section is just going to be 1 O and then C, H2 here. For suggesting the structure of the intermediate for part D, butane 2,3-diol is just going to be OH, OH, and when it reacts with iodine, basically what I'm expecting is for the iodine to keep having its oxidation state of, sorry, that's an I, having its oxidation state of 7, so it's going to have the remainder of its OHs from the ortho state H and double bond O, because if the other ones were double bonded, if it was in its meta state basically, then it couldn't have 2 different single bonds to an O. So for the next part, for part E, we're introduced to a new way in which the algorithm we were first introduced to applies. We're in fact very, very kindly guided through the algorithm part I. So the aldehyde A becomes OH. The double bond O splits into two OHs, so we have OH, OH, and ketone B becomes OH, again splits into two OHs, OH, OH, and then continues on. Section we're asked to apply the algorithm that we were taught before to these molecules. So part 2, we have a double bond OH, and then double bond O, that's C, with this OH, and then we have an extra OH, which we chuck into here, and then this is just an H. And then same story for this molecule, so we have a double bond, and then double bond, this extra OH, OH, and the two C bonds, so these two are different molecules. So here again, they're just asking us to apply the new harder version of the algorithm. I'm going to do exactly that. OH, separating them into OHs, because that's what the first part of the question here taught me to do, and I think I'm going to find it useful. Then I'm going to look at the bond between these two, and I'm going to sort of ignore the fact that there's two adjacent alcohols here, and this gives me this part becomes an OH, an OCH2, and then this section becomes this becomes a double bond O, then this extra alcohol becomes an OH, and then we have OH here. Now I'm going to assume that this is going to be D because it doesn't react further, or at least I can't see how it will react further, and this is going to be C because it does indeed have two adjacent alcohols, and so it can react with this thing. So when C reacts with the two adjacent alcohols over here, this alcohol becomes a double bond O, so we have CO, and that's CO2, and then this section will react exactly how this section did, so that's just going to be double bond CH and H. So compound C is OH, H, compound E is CO2, and compound compound D is this, compound E is CO2, and compound C is the one that will react, so OH, double bond O, and H. For part G, that's just a whole bunch of working. I'm going to start with the very left-hand side, giving me OH, OH, just separating the aldehyde OH, and a whole bunch of OHs here. OH, OH, and final OH here. And this will give me over here, that's going to be a double bond, the OH from when this bond breaks, the OH here will become a double bond C double bond O, and the OH here will remain an alcohol, so that's going to be this, and then the rest of the compound is going to become aldehyde OH, 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 and OH here. And what's good about the aldehyde here is that we've basically returned to the same type of of organic molecule, except we've removed one carbon. So again, if we continue this process, we remove this carbon, we make another one of these, so methanoic acid. So this gives a methanoic acid, methanoic acid, methanoic acid, methanoic acid. So that's 1 plus 4 methanoic acids, 5 of these, OH and H, and then finally reacting the whatever's left here with the adjacent OH, we have this part becomes methanol plus 1 times 1. For part 2, we don't have such a nice reduction thing, but let's have a look at what we do have. So OH up to, instead of going to have to separate it into 2, OH, down OH, up OH, down and H. This one is going to give me an ethanol an ethanol, H and H. This is going to give me an acid, OH, and dupe, OH, OH, OH. This acid here, when it breaks off, is going to give me carbon dioxide, and here I'm just going to get an aldehyde, and OH, OH. Oh no, sorry, I forgot to add the OH, and OH. And then we get to the aldehyde form, so this is going to give me, this molecule is going to give me a methanoic acid, methanoic acid, methanoic acid, so 3 times OH, H, and 1 times CO2, and then this one is going to give me the same aldehyde, so 2 times, oh no, you can't see it here, plus 2 times methanol. Everything's consistent. So for fuculose to react with periodic acid in a ratio of 1 to 3, we need exactly 3 bonds in fuculose to be broken, and there are a total of 4 bonds, A, B, C, and D, that can break. So let's see which combinations of these bonds can break with one of the one of the OH groups being replaced by a phosphate group. So we can break A, B, C, because then the only group that we don't want broken is B, and to do that we just replace the OH with phosphate group. We can't break A, C, B, because to not break B we need at least one of these two to not be broken, but to break A we need this one to be an OH and not a phosphate group, and to break C we need this one to be an OH and not a phosphate group. The same argument applies as ACD applies for ABC. ACD and ACD and ABD, and then it doesn't apply for DCB, because if we don't want A to be broken, then all we have to do is replace this OH group with a phosphate group, and that will stop A from reacting, and it won't stop any of the others. So, redrawing the two options, we have debreaking, in which case this group is the phosphate group. Just if you're confused about what the phosphate group is, by the way, H3PO4 has a phosphate group, that's the PO43-, and so the phosphate group, 3 of the oxygen in the phosphate group have to be O-, minuses, and then the last one is double bond O. So here, when it's bonded to the oxygen, it's going to be a P, a double bond O, and then 2 O- here. Minus, then double bond O, OH, sorry, I can't really see behind my hand, OH, OH, and nothing, and then same for the phosphate group when it's on this oxygen. That's going to give me an OH down to ketone, OH, OH, and O, then P double bond, O-, O-, and nothing. So these two are the structures that are consistent. Indicate which, on your structures, which CC bond would be broken in reaction with periodic acid. Well, we have determined that here it would be these 3, and in this case it would be these 3. For part J, the structure of the phosphorus-containing product, let's look at the 2 possibilities for the phosphorus-containing product. It could either be double bond O, OH here, and a bond to the oxygen, P. Now the O- are replaced with OHs, so OH, OH, and double bond O. or it could be this group, in which case that's just going to be an OH group and O, P double bond O, OH and OH. Looking at masses, to determine which one it could be, here we have the percentage of carbon by mass is going to be 2 times 12, which is the total mass of carbon, divided by 31, the mass of phosphorus, plus 6 times 16, the mass of the oxygens, plus 2 times 12, plus 5, that's the mass of the hydrogens, times 100, because it's a percentage, which gives me 15.4. Yay, so this one is consistent, and because they hint that it's only one, you don't really need to check the other one, but in case you started with the other one, I'm going to calculate the percentage by mass of carbon here, so that's going to be 3 times 12, because there's 3 carbons, divided by 31 plus 5 times 16, because there's 5 oxygen, plus 3 times 12, plus 7 carbons times 100, which gives you 23.1%, if I'm not wrong. Hence suggests structures from part H that are consistent with this observation, while this one is the only one consistent with the observation, because it's the only one that has a mass of carbon of 15.4%. So this will be the structure from H, which is consistent reaction. Thank you guys for listening. I hope you had lots of fun.